Okay, so welcome back. So let's go ahead and take a look at the course activity, Polynomial Identities for Unit 2 of the Algebra 2 Semester A class. So in this course activity, we're going to go ahead and look at expanding polynomials, but with a higher degree. So we've seen a little bit of like x plus 2 raised to the 2 power. We're going to see it larger as in to the 4th power, to the 5th power, maybe even to the 10th power. So let's go ahead and take a look at that right now. So we are going to start up with a quick little warm up on side 4, which is just to match up. I think it is to match up. Yes, it is. You're going to drag the tiles that correspond to its equivalent form. So they did give you at the very top the expanded form. You're going to go ahead and drag along the ones that are more simplified. So the idea for this one is that in this case, if you're looking at this one, you can go ahead and apply the banana method, or in other words, FOIL or distribution method, to find your equivalent format. Same thing with this one. You want to go ahead and distribute. And then for the other two, here there are one or two ways you can go ahead and try to factor it on your own. This one, I think I would wait for the last. Try to go ahead and use this one by actually, well, grouping help is the question. Actually, grouping won't help in this case, but I can kind of give you a hint already that these two, so the first two, you're actually going to go ahead and multiply. The other two, they're already expanded, but these two need to be expanded. So you can go ahead and expand this one. So I'll do the last one right here, which is 2x plus 3y, parentheses 2x plus 3y. And if we, again, the reason why I wrote it out 2 times is because of that 2 right there. This one, you would expand it and write it out 3 times. But if you, again, wait for that one to be the very last, you'll go ahead and see you'll have the other ones already set. And then it's just a process of elimination. You'll be only left with one tile there. So it'd be 2x times 2x, which will give us 4x squared. 2x times 3y is 6xy. 3y times 2x is 6xy, and 3y times 3y is 9y squared. So you guess you can kind of already see which tile that one is going to belong to. You just need to simplify the 2 middle terms in there. But either way, go ahead and take a moment to go ahead and do that. You should already be familiar with it because we've learned about expanding polynomials and multiplying them, and also simplifying. So again, this course activity is going to bring up some new topics that we haven't seen. And the idea is that they want us to figure out how to expand. For example, right here, it's a plus b to the 5th power, to the 7th power, to the 10th power. So imagine writing out a plus b, a plus b, a plus b, a plus b 10 times, and then going ahead and multiplying all that. You are going to get, it's going to get a little bit messy. And also I can kind of tell you, because it's raised, I'm going to specifically hit the 10th power one. A plus b to the 10th power will give you a total of 11 terms written out. Now keep in mind, when you multiply it all out, you're going to be able to combine like terms. But once you're done combining like terms, you're going to have a total of 11. So it's always, by looking at the power, you can see that it's always going to, if you add 1 to it, you're going to, that's how many terms you should have. So that's another way of checking. So if you do a plus b to the 5th power, you'll have a total of 6 terms. Here, they did an example for us, which is 2x plus 1 raised to the 3rd power. Again, because it's raised to the 3rd power, if I add 1 to it, we get 4. If you look at the final line in that yellow box, we have a total of 4 terms. So again, that's just like a quick little note to get an idea. But the thing is, we're trying to make our lives just a little bit more simpler when it comes to this. Now, we can do up to the 3rd power and multiply it out, but what about to the 5th and the 7th? There's a lot of room for error because, again, you've seen it with a couple of times where I've made an error, and it's and it's by slight little thing. Either I copied it wrong or I miss a sign. So that definitely affects um, our answers here. So we take a look at this one on side 6, proving polynomial identities. You should actually already have these written within your notes, especially covering the first couple tutorials that we've seen in the unit 2. Difference of squares, difference of cubes, sum of cubes, perfect square. Now remember, perfect square, I have like a, I'm like, I like it, but I dislike it at the same time, because we can expand by multiplying, or we can, if we have the expression we need to factor it down, we can use the giant X. Then we have the perfect cube, and that is very similar. Actually, perfect cube is probably the only one that's new to us. So I definitely suggest that you should have that written in your notes, just in case we go ahead and encounter that within the next couple of slides. So let's go ahead and move into slide 11, or slide 7, sorry, slide 7. And here they're asking us to go ahead, what is the simplest form of this binomial expression? So one or two ways to solve this, right? When you're taking a test and you have multiple choice, if you're very unsure that you don't know how to break this apart, you want to, if you have multiple choice, you can technically multiply those all out and see which one gives you the final result at the top, a to the fourth power minus b to the fourth power. But we don't have to do that necessarily. This one, I'm going to give you a hint. Use the difference of squares first. And remember, when we practiced it a lot with cubes, we identified the a and the b. Now, when we did the cubes to find a and b, we took cube root. Here I'm telling you to take the difference of squares. And then even from there, you're going to do one more step on factoring one of those parentheses. So if you identify your a and your b, you're going to, the a is your first term, so this is a to the fourth power. Your b is your second term, which is b to the fourth power. And again, like I said, difference of squares, you're going to take the square root of each term. And by taking the square root here, you have a squared, and taking the square root of b to the fourth, it is b squared. So go ahead and apply that using the information of difference of squares. And again, you're going to expand it one more time. Let's take a look at slide 8. Again, remember, don't forget that you're going to go ahead and pause the video and work on it, and then just come back straight to it. Let's take a look at this one. This is one that is new to us. From in the previous tutorials, we haven't seen the perfect cube identity, as you should have written it in one of the slides. They gave us that they gave us that identity and formula setup. We're gonna go ahead and take a look at it. I'm not gonna focus too much on it, because they it's not, it is good to know, but we're not, I think this is the only time they actually bring it up within the tutorial, or I mean within this course activity. It's not going to be applied to to other questions. But let's go ahead and I take a look. So remember, for cubes or squares, we want to identify a and b. A and b are normally related to the first term. B is normally related to the second term inside. So right here, a, again, is the first term, which is your 2x. B is related to your second term, 3y squared. So now that we know what a and b are here, we're going to apply it to this expansion over here on the right-hand side. So if I'm going to enter my a here and raise that to the third power, then it's going to be plus 3 parentheses a to the 2 power times b, plus 3, and this is going to be a to the 1 power, and then this is b to the 2 power. I am making no more space for myself here. And then I have plus b, oops, you know what? I take that back. Let me rewrite this up here. Give me a moment to go ahead and write this out. Okay. So what I did is I rewrote it, and actually where I have actual space. So by taking a look at this right here, again, we already identified, oops, why is this popping up here? There we go. Okay. We want to go ahead and identify our A and our B. So we figured out that our A is that 2x. So that's where we're going to fill in inside the purple boxes there. So that is going to be my 2x, 2x, 2x. And then our B is in green. That's my 3y squared. So I have my 3y squared, 3y squared, and my 3y squared. If, like I said, math has its, sometimes have its patterns. I like to look at the patterns. But if you notice with the purples, look at the powers. If we go over here, and I'm pointing my finger, like if you can see my finger, right here, purple is raised to the 3rd power. And then on the next term, it's raised to the 2 power. Then it's to the 1 power, and then it disappears. Do you see how it's a countdown? 3, 2, 1, gone, 0. Look how the green works. Here it's gone, so 0, then it's here at 1, then 2, and then 3. That 3 is, so the first term, or A, starts out with 3, and then it decreases, and then our second term, which is our B, it actually starts from 0, and then it starts to increase. So it works like the opposite way. So again, what I did is we identified A and B, and then we plugged it into the formula right here for perfect cube identity. Now it's just time to simplify. So if I raise 2 to the 3rd power, that is 8. X to the 3rd power is x cubed plus, right? So I have 3, 2. So I'm only focusing on the coefficients first, and then I'll go ahead and take a look at the variables. But like right here, I have 3, 2 to the 2 power is 4, so 3 times 4 is 12. And then I have this 3 here. 12 times 3 is 36. This will give me x squared. And then I have y squared. The next term is plus 3 times 2 is 6. This is 3 squared for 9. 6 times 9 is 54. And then I have x, y to the 2 power plus 3y squared raised to the 3rd power. 3 to the 3rd power is 27. And then right here we have, ooh, I messed up already here. This would be y to the 6th power. Now, give me a moment here. This is good. That's x squared, y squared. I messed up the second to last term. It is not y squared. It is y to the 4th power because it's y squared raised to the 2 power. My mistake there. Sorry. So if we take a look, they also identified A, B, and C, or I mean A and B, sorry, just A and B. And then they plugged it in and they expanded and simplified. They also got 8x cubed plus 36x squared y squared plus 54x y to the 4th plus 27y to the 6th. So again, for some of these identities, it is best to identify A and B first, and then you go ahead and applied into the expansion. So let's go ahead and take a look at slide 9. It is another identity, and they're actually telling you which identity to use. So again, if you just identify your A and your B, you're going to be able to apply it. It is the sum of cubes. Now, here you're in the last example we just did right now, we expanded this one. Here it's already expanded. We're trying to factor it down. So write your answer in the form of the expression on the right of the sum of cubes identity. The sum of a cube's identity. Okay. So if you recall that the sum of cubes identity is A plus B, parentheses, then it is A squared minus A times B plus B squared. So again, all we gotta do is just identify our A and B. So keep in mind our A and B squared, or I'm sorry, keep on saying b squared. Our a and b are cubed, so we're going to take the cube root of those two terms there. So the first term represents my a, so I will get my a here is equal to, well, don't remember, it's not quite equal to 8 to the 6th power. I have to take the cube root of that. So if I take the cube root of this, cube root of 8 is 2. Cube root of x to the 6 is x to the 3rd. Now let's go ahead and move on to finding our b. So our b is using that second term, 27, y to the 3rd. Again, if we take the cube root of that, the cube root of 27 is 3. Cube root of y to the 3rd is y. So now you're going to plug in your 2x cubed for a in the identity above, and you're going to plug in 3y for your b. Make sure you simplify properly, and then you're just done right there by plugging it in and simplifying, and then typing in your answer there down below for slide 9. Moving on. So we're going to go ahead and discuss the binomial theorem. It's not the nicest thing to look at. I'm going to say that. But at least we do know with the powers is that, again, if we have x plus y raised to the 2 power to the 3rd power, we don't have no problem multiplying it all out. But when it gets higher to the 5th power or even to the 10th power, there is a couple of theorems that we can use to kind of help us figure out each of those terms without doing that whole multiplication of drawing out the lines. And remember, as I think I've messed up before where I drew the lines and I think I had an error because I wrote the problem down incorrectly. So there is a lot of room for error, only because it can just get, when you're writing it down, it can just get so messy. But we're going to use this binomial theorem where it's going to help us for any expansion of any higher power. So like I said, we can easily do the raised to the 2 power, raised to the 3rd power, but anything higher than that, or we can still do 4. But we're going to, in case we encounter to the 6, 8, 10, 12, anything higher, we're going to use a binomial theorem to help us out here. So on slide 11, and like I said, it's not very pretty to look at, but there is a pattern to expanding. So we do have our a and b, which again, a is the first term, b is our second term, and it's raised to the n power. So when it's raised to the n power, again, n can be any number. In this case, they expanded this one of 5. And remember, because the degrees the exponent is up to 5, that tells me I'm going to have 6 terms. It's always one up. So if you count them, here are your 6 terms. They actually use the formula and break it apart. So the idea is this is 1 term, this is 2, this is 3, this is 4, and if you realize, it's going to get bigger and bigger and bigger. And also notice the pattern here. Maybe within the first 2 boxes, you can't really see the pattern, but between the second and third term, you can kind of start noticing something. So it's going to be n, whatever that value is, right, over 1 factorial. Factorial is actually something new as well that they're bringing up here, and I'll go ahead and explain that right before. But then the idea is just focus on that part first, n, and then it's n minus 1. You move on to the next term, it's n minus 1, n minus 2. Do you see how we can find, now these 3 dots means that it can expand forever, but we can come up with the next one just to get an idea. Inside here, right, or after this box here, it would be n, parentheses, n minus 1, n minus 2, n minus 3. All over. So then look at the factorials. This didn't have a factorial. It's 1 factorial. I know it was like you're in an English class, it's an exclamation point, but here in math we call it a factorial. It'd be 1 factorial, 2 factorial, 3 factorial. That means that this is 4 factorial. Then let's focus on the a. So it's a to the n minus 1, a to the n minus 2, a to the n minus 3. The next one would be a to the n minus 4. Let's focus on b. Here, there's no b. So like I said, in the first 2 terms, it's not that clear to see, but let's go ahead and take a look at the next one. B to the 1, b to the 2, b to the 3. This means that this is b to the 4. So keep in mind, this one goes right here in the middle, and then it continues on until the very end of b to the n. So that is the binomial expansion. Now, let me discuss the factorial. Or actually, let me take a step back. We know what A is, we know what B is. Again, A is the first term, B is the second term. N is that degree power that it's raised to that we'll be plugging in. And do you see, we can, by following this pattern, we can find the next term and the next term and the next term. Do we really want to do that? Not really. If this one right here in red would be the 1, 2, 3, 4, this would be the 5th term. So if you think about it, if the 5th term, do you see where I'm kind of stopping at? Where because it's 5, this is 4, 4, 4. So it's whatever term you're on, it's 1 less than that. And it's like, if you don't see the pattern, that is completely fine. It's just things to kind of notice. Again, I'll be helping you write out some of these formulas so you're not really on your own for this part. Because again, this is a new material. Are you going to get tested on this within this unit? You are not. This is for this specific course activity. They're bringing you, it's like a tutorial combination with like, all right, let's teach you this new material very quickly, and then let's go ahead and jump into it and work on some problems with it. So this is the only section where you're going to see it here. So are you supposed to like fully grasp onto it? Not entirely, and that is okay. It's like I said, it's an eyesore, but again, sometimes it helps when we can identify a pattern. You notice that I like to color code or I like to highlight things, but again, also the beautiful thing I like about math is that the patterns. It's kind of like a little puzzle, and I like puzzles. So, but if we can find a pattern to kind of help a little bit with this, and see it. But again, if you don't clearly see it, that is completely fine. Again, you're not going to be alone on for this one, because again, it looks intimidating at first sight as well. So going back to this. Now, this is specifically the 5th term. Let's take a look at this one, which is the 4th term. Do you see that idea that I'm trying to bring up where the factorial is raised to the 3rd power? It is always 1 less than the actual term it's supposed to be. Do you see? 3, 3. Now here it's n minus 1, n minus 2. It's written out 3 times only per factor. That's kind of what I wanted to point out. Let me introduce factorials. It's not, it's actually not entirely bad. So if I were to write out, I'm going to start with like a semi-large number, 6 factorial. If I'm given 6 factorial, this tells me that I'm starting with 6 and I do a countdown, but I have to multiply these numbers. So it'd be 6 times 5 times 4 times 3 times 2 times 1. And you multiply that all those numbers out, you get your 6 factorial. So like 6 times 5 is 30. 4 times 3 is 12. 12 times 2 is 24. Times 1, still 24, so we already included that. And then this is 12, 6, 7, 720. Oops, 720. Now, if you're uncomfortable with the factorials, you can go back into using the scientific calculator through Desmos. Again, it's DESMOS.com/scientific, Or if you go into Google and type in Desmos Scientific Calculator, it is one of the user-friendly ones here. Just to confirm that I did 6 factorial correctly, I'm going to type in my 6. Now, if you're uncomfortable typing it onto the keypad, you can go over here to functions. Is it under functions? Yes, it is. So, oops. Don't want that. Okay. So here's my factorial symbol, or you can just type in the exclamation point yourself. And they also got 720. So remember, it's that number and you're doing a countdown, but every single number you're writing is you're going to go ahead and multiply. So let me just give one more. Let's do 4 factorial here. So 4 factorial is 4 times 3 times 2 times 1. 4 times 3, we get 12. 2 times 1 is 2. 12 times 2, we get 24. But it does get a little bit ickier when we're writing a very, very large number, right? Yeah. So let's go ahead and move on from here. So we're going to go ahead and move into slide 12. Actually, before I do that, there I mentioned about a pattern in one of the questions earlier. I think it was like on slide 9, identifying a and b for the sum of cubes. And I was trying to point out how a was decreasing in power and then b was increasing in power. Let's kind of that same idea happens right here, mainly with those variables. So again, they are using x and y here. If you notice here, or actually I'll write it out because I like to just write it out bigger. For the first term, your x is the first term, so it's going to be x raised to the max power is 5. And if you think about it, for every term, it's going down. So x to the fourth, x to the third, x squared, x, and then it would be technically x to the 1 and x to the 0. Anything to the 0 power just becomes 1. We don't have to write it out there. Now, if I continue, this is going to be, remember that idea, y to the 0, y to the 1, y to the 2, y to the 3, y to the 4th. Here, if I put my x to the 0, this is just y to the 5th power. But remember, anything to the 0 power is just 1. It swaps out. You don't really have to have it written there. But you see how that pattern matches up for each single term. And again, because it's raised to the 5th power, you should have a 1 up. 1, 2, 3, 4, 5, 6 terms. So now let's go ahead and move into, take a moment to go ahead and actually write out this equation. It's going to come in handy because we're going to actually use it for one of our questions, I think within slide 13. So please go ahead and take a moment to write it out. Again, you don't have to write it all out. You can write out the one where I had a little bit before, where we wrote it for 1, 2, 3, 4, and the 5th term, and then just write, put dot, 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 and then b to the n. But we are going to be using this for the next couple of questions here. So that idea that I mentioned, that it is one of the variables is decreasing by power and the other one is increasing by power. They're actually kind of stating that here. Now here's another thing that I probably should have mentioned. Because it's to raise to the 5th power, look at all these exponents. 5 plus 0 is 5. 4 plus 1 is also 5. 3 plus 2, 5. 2 plus 3, 5. So whatever power it is, if you add the exponents, it should lead you to the same amount of powers raised to that. Now that is a different case. If this was not just x, it is x squared. That would be a different story. It would be a little bit changed compared to this idea that we're seeing. But 1 plus 4, also 5. This disappears, so it's just 5 right here. Same idea how it happened at the top, or you can just do that 5 plus 0. Again, it's just connecting things together. And to relate to certain patterns. So now let's go ahead and take a look at it at slide 13. Um, so what happens if I don't want to expand everything? What if I'm looking for a specific term? So in order to find a specific term, or the rth term, which is for the binomial expansion, this is going to be our formula that we're going to use for it here, which is this one right here. Again, I am not the biggest fan of it, but we are going to go ahead and write that one out as well, because we're going to actually see that in the next couple of slides. So go ahead and make sure you take a moment to write out finding the rth term. And if you like to, go ahead and take a look at how they determine this one for the sixth term, by looking at this one. Again, it's not, they didn't write out everything, because I don't like that they didn't write out what goes in between to actually see what's going on. Just know, yeah, I don't like this. I don't like how they presented this example. Go ahead and make sure you write it. But again, I will go ahead and make sure I help you out for the next couple of questions, and at least giving you the setup for it. So let's go ahead and move into slide 14. So slide 14, it is the scoring for each task that we're going to see that is graded. So let's go ahead and take a look at task 1, which is on slide 15, where we're going to use the binomial theorem. Just give me a moment to make sure. It's only 3 questions, but we're going to go ahead and expand it. So like I said, you can multiply this all out. If you take a look at it, we're doing x plus y raised to the 4th power. But the idea is that they want you to apply the binomial theorem. So we are going to use a binomial theorem and expand it. But so the idea is that we're trying to avoid the whole x plus y times x plus y times x plus y times x plus y. So for this one right here, remember how I said if it's because it's raised to the 4th power, we're going to have 5 terms. So you can kind of already eliminate this one, right? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So you have 3 of them. You're only selecting one. Again, you're only selecting one. The question is, which one? So let's go ahead and apply it here. Now, if you also take a look, this is your first term, second term, third, fourth, and then you have your 5th term. So they already gave you the formula. You just need to identify what is your A, what's your B, and your A, B, and your N. So I'm going to help out with the first couple ones, but let's go ahead and make sure your A is your first term, which happens to be X. So we'll make a note of that over here. A is equal to X. Your B is your second term inside the parentheses, which happens to be your Y. Your N is that power there. So that is going to be the 4th power. So we just fill it in. So first it is, let me see, you know what, let's give me more room here to see. So it is A to the N power. So it's X to the 4th power. So we have our first one here. Plus, now it's going to be N over 1 factorial. So N is 4. 1 factorial is still 1. And then this is going to be A to the N minus 1. So in this case here, it's 4 minus 1. Then it's B. Oops. See, I accidentally did something here, right? I didn't write my X for A. I just wrote A. We know A is X. So this is X to the 4 minus 1 power. And then this is going to be B, which is Y to the 1 power. So we are I am only filling it in. All we got to do is just simplify. Moving on to this third term, plus it's going to be n, so that is 4. Then it's n minus 1, or 4 minus 1, over 2 factorial. And if you think about it, if we handle 2 factorial right now, 2 factorial is the same thing as 2 times 1, which is 2. Then it's a to the n minus 2 power, or the 4 minus 2 power. And there you go again with the a. Oops. All right. This is, sorry, a again is x. Then it's 4 minus 2 parentheses, and then it's b, which is y to the 2 power, plus, and here we go again. So this is 1, 2, 3, 4. So we're on our fourth term. So it's going to be n, which is 4, parentheses 4n minus 1, so 4 minus 1, n minus 2, or 4 minus 2, all over 3 factorial. So instead of writing out 3 factorial, we can just go ahead and try to simplify this. So 3 times 2 times 1, 3 times 2 is 6, 6 times 1 is 6. Now this is a. I just really want to write a this time. So this will be x raised to the 4 minus 3 power. And then this is y raised to the 3 power, plus our b is y, and our n is to the 4th power. So if you see, we have 1, 2, 3, 4, 5. So those are 5 terms, but the thing is, it doesn't actually match up to what we have down here. All we got to do is just simplify. So I'm going to leave you to go ahead and do that. Here, this first term is just x to the 4. All you got to do is take care of this. So like 4 divided by 1, that's just 4. That'd be x. 4 minus 1 is 3. And then this is y to the 1 power. And you continue. Make sure you handle inside the parentheses. So 4 minus 1, 3. 4 times 3, 12. 12 divided by 2 is 6. X to the what power? So go ahead and continue on that, and then select your correct one. Again, if you're still not sure about it, or you're still like iffy, you can go ahead and multiply x plus y by writing it out 4 times and then expanding using distribution method. We're going to go ahead and move on to the next question, number 2. So here it says, what is the eighth term of the binomial expansion x plus y raised to the 10th power? So this is the formula we're going to use that is for our rth term. And do you see, we don't have to expand it. So we don't have to do all the work like we did for this one. All we have to do specifically is for the 8th term. So if I 2, 4. So remember how writing out this setup to finding out that 8th term, I'm not going to use where they actually write out, I think it was from slide 13. I don't like how they wrote out the expansion of it. So I'm going to write out the fully expanded. And what I want you to do is you're going to identify your A for me, your B, your N, and your R, which we'll go ahead and write out. And then you're going to go ahead and plug in for me. So let's go ahead and take a look at this. So our A is your first term inside the parentheses in there. So that's your X. Your B is your Y. And then your N is that 10 there. And for the R, you're looking for your 8th term. So your R is 8. So you're going to plug all this information here. So all this info, and you're going to plug it into this. So you're going to apply it to this one here. So it's n minus 1, n minus 2. I'm sorry if my n's look like h's. I try to make them look like n's, but then sometimes they look like an h. And then it'd be n minus 4 and minus 5. Ooh, it's a countdown, sorry. 5, and then it's n minus 6. So I'm using this information based off of the pattern that I was trying to point out earlier. So because we're looking for the 8th term, we're gonna do one less than that for the 7. So it'd be 0, 1, 2, 3, 4, 5, or I'm sorry, 1, 2. We're not gonna start 0. 1, 2, 3, 4, 5, 6, 7. Then it's gonna be all over the R value minus 1, and that's going to be the factorial of it. And again, if you're unsure, what you're going to go ahead and do is that you can write this out in paper, but instead of writing the n and r, you're going to replace it with the actual number values in there. So obviously for the n, you're going to replace all those numbers with 10, and then you have to simplify. Here, it's going to be 8 minus 1 over, or 7 factorial. Now remember, 7 factorial is going to be 7 times 6 times 5 times 4 times 3 times 2, and so on. So in this case here, you might want to use a calculator to go ahead and help you out. Then it's our, then here it's a, which we already know what a is equal to. A to the n minus r plus 1. So that is, okay. And then this is going to be b to the r minus 1. So again, all you got to do is replace those values for a, b, n, and r. And once you have it all simplified, you're going to actually find your final answer there for this question 2, part A. Now let's go ahead and move in to part B. So what I'm going to do is we're going to do this a little bit differently. I'm going to bring up that idea about expanding, and specifically, I'm not going to care about the coefficients. I'm just going to ignore them for a moment. But the idea about the pattern. So to me, it's very difficult to see the pattern horizontally. I'm going to write it vertically. So we know our first term, x, is the one that's going to receive the 10th power. That's our first term. And here they're actually asking us, well, what number term this one is, because again, it goes in order. So remember, the first term is starting to decrease in order. So it goes from 10, this is x to the 9, x to the 8, x to the 7, x to the 6, x to the 5th, and it's going to continue going down all the way until 0. So x squared, x to the 1, x to the 0. Now I know it's not completely straight, but we're going to take a look at our b term, which is y. And remember, this is y to the 0, and then it starts to increase, y1, y2. And remember, those exponents have to equal to 10 because that's the highest degree power that we have. So that is, if you see the pattern there, y to the 4, y to the 5th, y to the 6th, and I'll let you continue on. But which one has x to the 8th y squared? Now, again, I didn't focus on my coefficient of 45, but isn't my x to the 8th y squared right there? So if I count the terms, right? First, second, third. This is my third term. Go ahead and continue following the pattern for the y and find out the next patterns there for me. And that is it for side 15. So now let's go ahead and move on to the next couple of sides here. So we're going to go ahead and discuss Pascal's triangle. So Pascal's triangle uses a combination of, these are the coefficients, part of the coefficients that you're going to use to multiply that a term and that a and b, including the increase and decrease of those powers of the variables. If you can kind of see, it looks like a little kind of like the honeycombs hives thing, where it's kind of set up like a window thing, where we start out with 1. This is our degree power of 0. 1 in you noticed too that the side of it starts with one and it ends with one. So here it's 1 1. You won't see it now so much until you see it, but or oh my goodness, I didn't say that correctly. I'm sorry. The you won't see the pattern until we start getting much more lower, but this is for a degree of 0, degree of 1, degree of 2, right? So the first one top is 0, then it's 1 2, this is 3, this is 4, and this is 5. Remember how I said if we have a degree power of 4, I go up 1. That's telling me how many terms I have, which, so 4 plus 1 is 5. 1, 2, 3, 4, 5. Those are your 5 terms. So you're going to use those numbers embedded. But how do we come up with those numbers? So like I said, as we get a little bit more lower, you're going to see we start out with 1. And to find this next number, I use these two. 1 plus 2 is 3. Then I move on to the next one. 2 plus 1 is 3. Then, because there's no other one to hang on to, it's just 1. Here we start out with 1, then it's 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. And then we end with a 1 there. Same pattern. Start with 1, then from the top row, 4 plus 1, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. And then there's no other one to hang on to, so it's just 1 at the end. So now we kind of see a little bit about Pascal's triangle. They're gonna go ahead and describe the build of it. Like I said, it's kind of, you start out with 1, then 1 and 1. Here it's 1, 1 plus 1, that is your 2, and with 1. Then it's 1, 1 plus 2 is 3. 2 plus 1 is also 3, and then 1. 1, 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4, and then 1. And then again, starting from the very top, we start with the degree power of 0. Then the next row is 1, next row is 2, next row is 3. So that's what they're describing there. Let's go ahead and move into slide 18. So this will help us expand if we know the row that we're using. And then what we're going to go ahead and do is that we're going to expand it. Now remember that idea about the variables, that the first term variable starts out with the highest power and then it starts to decrease. The second term variable will start with 0 and then it starts to increase until we get to our highest power that it is set up to. So let's go ahead and take a look at it on slide 19 here, which is task number 2, which is also graded. Okay. So we are asked to go ahead and expand 2x cubed plus 3y squared raised to the 7th power. So the first thing we need to do is determine our a value and our b value. Our a value, so this is very different when we're finding a and b for the sum of cubes. Here, we're just picking it straight from there. So whatever is your first term inside your parentheses, it is your a. Whatever your second term is, that is your b. So again, so that first term, right, your a, then this is your b. Because we're going to use the same rule applies as this is like a plus b raised to the 7th power. So again, these new concepts that we're learning it only applies to this specific course activity. The rest, you're not going to get tested on it. They're not going to bring this up in the other stuff. So now let's move on to part B. So because we're using it up to the 7th power, we want to find the degree power 7. So remember, starting from the top right here, this is starting with 0. This is 1, and then this is 2. Go ahead and find me. So continue counting until you get to 7, and then you're going to select the row. So do you see it's selecting? The thing is, you want the one for the 7th degree. So it's not the one that I'm selecting because, again, remember, this one starts with 0 and then it continues increasing by 1. Go ahead and select that. Moving into part C. So part C, they told us they actually gave us the first 4 terms of the expansion of the binomial 2x cubed plus 3y squared raised to the seventh power. You can use binomial theorem using the rth term. Could be a little bit time consuming, but if we can use our knowledge that we have based off of the information about finding this each of the rest of the terms. So remember here, this is going to be one, the first term, second term, third term, fourth term, which they already gave us. This is going to be the fifth, the sixth, the seventh, and I'm just going to add another one up here. So we have 8 terms there. Now, if we have selected correctly from part B, the correct coefficient, which is starting with the 1, 7, 21, right? Let's go ahead and write those numbers there. 1, 7, 21, 35, 35, 21, 7, and 1. Those are my 8 terms from the expansion there. Now, they told us, they already gave us the first 4 terms. So that 1, 2, 3, 4. I need them there because they're like a placement to help us find the next couple of terms. Now, these terms are going to be multiplied with everything here. Now, remember, we identified your A. So what you're going to do is plug in your A value into this set of parentheses, which maybe I shouldn't make them that big only because we are going to expand them. But in the first set of parentheses, we're going to place our A value that we determined in the first part. And remember, because it's raised to the 7th, this is to the 7th power, 6, 5, 4, 3, 2, 1, 0. Then the second set of parentheses is your B value. And again, we determined that one in our first part of this question here. And this gets to increase, this one starts at 0 and then it increases to 7. So 3, 4, 5. Now, the reason why we're still using the countdown, but it doesn't really match up to that, right? To what we see there is because we don't just have x, we have x raised to the 3rd power. So that actually changes our situation here. But if you fill it in correctly and then you solve for A and B, you should be able to find the next one. So again, I'm going to help you figure out the 5th term, which is right here. Now we know that our A term is 2x cubed and our B term is 3y squared. How am I going to expand this? Well, I know I'm going to multiply 35, so I'm going to actually show my work over here. Again, I'm doing this box right here for your 4th term. Then you would continue finding your 5th term. So all we have to do, again, that's a y, expand. So this is 35. 2 raised to the 3rd power is 8. And then this is x raised to the 9th power. And the thing is, they didn't leave you completely, like, you don't see, you do see everything. No, you don't see everything. They gave you a portion of the answer already for part of the term. So all you got to do is make sure that you simplify simplify properly, and you should be able to find your missing number there. So then this is going to be, so I did this part. Now I'm going to do the second part. 3 to the 4th power is 3 times 3 is 9. 9 times, it's another 9, 81. So this is times 81. And then this is y to the 2 times 4 is 8. So remember with exponent, when an exponent is raised to another exponent, you multiply. So 3 times 3, that's how I got my x to the 9. 2 times 4, that's raised to the 8. I'm going to go ahead and move this over here to my calculator and multiply this out. So I'm going to go back over here to the main. So this is 35 times 8 times 81. And I get a value of 2,206 22,680. Then I'll move my variables to the side. So that is x to the ninth power, y to the eighth power. And that's my value right here. So now you're going to go ahead and continue. So you'll fill it in, right? This is still the same. These are all going to be the same. It's just when you're simplifying, it's going to look a little bit different. So go ahead and continue. It looks like you're doing it. You already got it. You already got the fifth term. You need the sixth, the seventh, and then the eighth. So you'll just be filling in the last three rows over here and then making sure you simplify. And then that will be it for slide 19. Let's go ahead and move on to slide 20 about the Pythagorean theorem. So the Pythagorean theorem we've seen a little bit in our geometry course, where if you have a right triangle, the two legs of the triangle. So pretty much what I like to say is that the leg makes up the L shape, right? Because it's a right angle, it makes a perfect L. That's your A and B. Does it really matter which one's A and B? No, as long as they're the legs. Your hypotenuse is a different story. Your hypotenuse is, so like I said, here's your L shape for the triangle. Here's is your 90-degree angle. It is always open up across. That's your C. Your C is the largest side of the triangle. And what we're going to go ahead and be doing here is that we're going to be applying the Pythagorean theorem and discussing the Pythagorean triples here. So I think they provide a video about the Pythagorean theorem through, so just giving you a couple examples of how to find a side, a missing side using the Pythagorean theorem, which we can kind of do this example right here. So again, we're going to apply it to this formula: a squared plus b squared equals c squared. The most important one is to identify your C. Your C is, again, the longest side, or right across from the 90-degree angle here. So that's your 10. Everything else can be flipped. This could even be considered your B. It's not as strict for A and B. C is super strict because, again, it has to be that larger side. So here they're going to call it A, which I'm fine with. So this must be our B. So let's just leave A squared because we don't know what A is. Plus, let's replace our B with 6. So it would be 6 squared equal to, instead of C, we're going to apply that with, or replace that with 10. So another way to like kind of see it is that you can just fill it in like this: a squared plus b squared equals c, oops, it's supposed to be a box, c squared. And then you just fill it in like, oh, we don't know this one, so that's a. Let's put this as 6. Let's put this as 10. Or they listed it for us, but it could be 6 first here, and then it's b squared. You're going to get the same value. But again, they listed this one as a. So then we simplify and solve for a. So nothing happens to this a squared. We do know that 6 squared is 36, right? 6 times 6 equals 2. 10 times 10, or 10 squared, is 100. I want to isolate a squared, so I'm going to subtract this 36 and get it away from a. And you always do with the opposite, it's happening right there. So plus 36, opposite of that is minus 36. You got rid of this, so this is a squared equals 100 minus 36 is 64. Now again, I just want a. I don't want a squared. So we get rid of the square by taking the square root. So by taking the square root, this cancels out the square. We're left with a equals square root of 64 is 8. So that missing side is 8. Now, if I were to write this out, because this is going to be introduced to you a little bit over here, the Pythagorean triples, it's 6, 8, 10. This is considered a Pythagorean triple because if I replace it into here, you're going to see a squared plus b squared. So this is 6 squared plus 8 squared equals 10 squared. If this is true, the statement is true, then this is considered a Pythagorean triple. So 6 squared is 36 plus 64 equal to 100. If I add these two values, we also get 100. 100 is equal to 100. So then not only does this right triangle works out because we found the missing value of 8, this is also considered the Pythagorean triple, because each of those values, again, your largest value is C, is going to be written off to the right hand side. The first two will be your A and B. Again, it doesn't matter what order it goes in for A and B, as long as your C is your largest side. Because we plugged it into the Pythagorean theorem and we got 100 is equal to 100, this is considered a Pythagorean triple. Um, so that's just a little bit going into that. Let's take a look at slide 21. So same idea here. I know I use an example based off of that, but you can go ahead and use your example there. Go ahead and identify what is your A, what is your B, and what is your C. Keep in mind your C is the largest side. You should look for your 90-degree angle and then drag your finger across. That is always your C here. Then again, this could be A or B. We'll just say A, this is B. So now you're missing A. Go ahead and plug it into the formula for A squared plus B squared is equal to C squared, and find that missing side. And I think that's what they're going to bring for you right here. And so now let's go ahead and take a look at this one. So do you have to rewrite the equation for this right here? No, I wouldn't. It is another way to go ahead and solve. But if you just follow those steps, like apply the square, here they're trying to isolate already beforehand. Um, you get the same results just following it. It's just written in a different way. You don't have to. Kind of like with the last two examples, or with that last example that I showed you from the separate link that they provided. That is more than enough. Here, they're just rewriting it. Do you have to do it this way? No. But you can go ahead and review it there. So the idea here, Pythagorean triples. So what we're going to do for Pythagorean triples is I'm going to give you a parentheses with three numbers in there. And the first two numbers should be your A and B. Your last number should be your C value, which is the largest side, and you're gonna go ahead and plug it into the Pythagorean theorem, which is A squared plus B squared equals C squared, and you're going to see if it works. Now, here's another thing too, that it is only positive integers. When I say an integer, it has to be a whole number for this to be considered a Pythagorean triple. Note that the list of Pythagorean triples in order from least to greatest, so the values will always, the value is always a hypotenuse. So, like I said, I know I say that A and B order doesn't really matter, but they're going to give you the list in from least to greatest. Your last digit should be the highest digit. Again, that's your C. The first two will be your A and B that you'll be plugging into the formula. So, again, when you plug in these values, some will work, some won't work. Sorry. So for the Pythagorean triple, remember I said a key thing, make sure it's an integer. So what they did here is that they have this triangle with two side lengths as 1 and 1, and then we have the square root of 2. So using the square root of 2, this is actually a special triangle for us that we use in geometry. But here, this one does not form the Pythagorean triple because the last number, which is the square root of 2, which is our hypotenuse, it is not an integer. That is a radical. We want whole numbers or integers, and they have to be positive. There's no negatives there. So let's go ahead and take a look at slide 23, where you're going to go ahead and determine those Pythagorean triples for me. So there is a list. You're going to go ahead and check off the ones that are considered Pythagorean triples. So again, you're going to fill it into this form of the A squared, B squared equals 2C squared, right? You'll fill in your A, your B, your C, and see if it's true on both sides. But if you can take a look already, I see one that doesn't even work already because it has a radical, this one right here. So you can kind of already ignore that one. Now, again, you just plug it in. So if we do the first one together, right? You plug in your 8, your 15, 17. You take the square of each of those values, add these two when you're done taking the square, and see if it matches up to 17 squared. So again, go ahead and take a moment to do that for slide 23. Move on to slide 24. So slide 24, it is task number 3. And we are going to go ahead and take a look. Let me just clean this up a little bit here. Okay. So going into part A, they actually give us uh, a triangle, and they want us to prove that, or actually I'll go ahead and like read it off. So in this activity, you'll relate the polynomial identities to Pythagorean triple. Answer the following questions based on this triangle with the side lengths of x squared minus 1, 2x, x squared plus 1. So there's your right triangle. Now here's, listen to part A. So it says prove when x is greater than 1. So as long as x can't be 0 for us because then it's no measurement. So it has to be greater than 1 and it stays positive. A triangle with the sine length of A is x squared minus 1, B is equal to 2x, and C is equal to x squared plus 1 is a right triangle. Use the Pythagorean theorem on the given sine lengths to create an equation. Use this equation to show that this triangle follows the rules describing right triangles. So if it is a right triangle, right, then A squared plus B squared should work for this triangle. And what is also helpful here is that they also told you what your A, B, and C are. So we replace A with x squared minus 1, plus we replace our B with 2x, and we put that squared equal to C, which is x squared plus 1. Now, keep in mind, this is also being squared. It says use the equation of the to show that the triangle follows the rules. Describe the describing the right triangle. Explain your steps. So I'm writing this on screen, but I'm going to show you a little bit of what you're going to be doing here to enter it. You are going to be using our button here for equation editor. So once you have the cursor typed in for part A, you're going to click on this yellow button here. And what you're going to go ahead and do is you're going to go ahead and type out this here. So again, we're starting with A, and use those power buttons. So if you take a look from the 4th button from the left, you'll type in A squared plus B, click on that to write your 2 power, bring the cursor down, right, equal to C squared. What happens if you don't bring the cursor down? It stays up as a power. Now, we already know what A, B, and C are. We're going to write out that second line. So for me, I think it's always been a force of habit that I just write out the setup. So keep in mind, you're going to want to use these buttons to make it a lot more cleaner. This has parentheses, and this is raised to the 2 power. So I'm going to fill in my A. We know A is x squared plus 1, so this is x raised to the 2 power plus 1. Then we have 2x, and then this is, oh wait, I'm already messing this one up. A is x squared minus 1, so be very, very careful. And then your C is x squared plus 1. So what did we do here? Again, you need to explain your steps. So right here, I'm going to put a semicolon, right? After all my work, I'll put a semicolon and say, and make the statement of what we did here. So we substitute or replace, right? Replace the values for A, B, and C. So every single thing that you do, you make sure on that same line, tell me exactly what you did. In this case here, again, you're trying to prove of the Pythagorean theorem here. So the next thing you want to do is actually expand this. So again, I'm helping you a little bit with this piece here. So x squared minus 1 times x squared minus 1 plus, this is going to be, well, you can already multiply that out. 2x to the 2 power is 4x to the 4th power equal to, and then you're going to expand this as well. Now, I've expanded, but I haven't multiplied. So what am I going to write here as my notes of what work I did? I just expand um, the form, the equation. So now what I want you to do next is to go ahead and multiply using distribution method, or like what I say is banana method. So then you're going to go ahead and expand that, multiply that out and write out your results here. And again, the rule for there is that um, distributing or just multiplying, right? Multiplying both sides, or just say multiplying. The next one is you're going to want to, again, you're telling me every single step here. Your next step should be to combine like terms. So once you're done expanding, right, multiplying slash expanding, because you're expanding it more, you're going to go ahead and combine like terms, and you're going to note when you combine those both terms. So remember, what you're multiplying, you're going to multiply this out. Then you're going to multiply this out and give me those results there. Nothing should happen to that 4x to the 4th. For the second part, you're going to combine like terms. So you're going to notice there's going to be some things after you multiply in this line here that you can combine like terms. Again, you're very familiar with that already from that first couple of tutorials that we saw in this unit for unit 2. And then you're going to prove to me, right? If one side, the left side should match the right hand side. It should match. And that just tells me that they are equal by using the Pythagorean theorem, which is what, like, explain, right? Explain what you see there. So you're not going to actually type this out there, but you're going to explain to me why this works. You're going to pretty much say like the left side, by plugging in those values, the left side matches the right hand side by plugging it into the Pythagorean theorem, meaning that this is a right triangle. So that will be for part A. Now let's, once you are done with that, so forgot one last important step there is once you're done, you're going to go ahead and click OK, and all your work that you have typed right there should be shown in the box below. Let's go ahead and move on to part B. So part B says, which identity is the result of using the Pythagorean theorem shown of the triangle with the side lengths of x squared minus 1, 2x, and x squared plus 1 is a right triangle? Technically, it's already written there for you, right? We plugged it in just straight into it. That's pretty much our first sign that we were coming up with in part A. So then we can go ahead. Please be very careful with the signs. That's my only hint on there for that question. Moving into part C. So for part C, again, I'm going to go ahead and help you with the first two, and then you're going to kind of follow the same steps to go ahead and find the last two. So actually, for both of these, yeah, or I'll help you out. So this one, for the, you're going to go ahead and find the Pythagorean triple. So what if we told you that x is 3? So what you're going to do is kind of solve these independently per side. So what I'm going to do here is they did tell you what your A is. So your A is, because remember your Pythagorean triple is parentheses. And please, please be careful. You need to type it in just like this. Your answer for Pythagorean triple should be A, comma, B, comma, C. The thing is, what are your A, B, and C's? Remember, A was originally for is x squared minus 1. Your B is equal to 2x, and your C is equal to x squared plus 1. Now, again, I said I know I was going to say it, like I'm going to walk you through it, but for this one right here and this one right here, to find my Pythagorean triples, all you got to do is replace the x value with 3. So I'll start out with this one here. It'll be 3 squared minus 1. That's 9 minus 1, 8. So far you should start out with you'll have one value as 8, and then you're going to continue on finding the rest. Make sure that there is a comma in between them, and it is from least to greatest. Please make sure it is least to greatest. So go ahead and make sure you do that for the first row and then the third row. Let's talk about the finding the x value, but they already gave us the Pythagorean triple. So let me kind of clean this up. Remember, least to greatest. So make sure you start out of all the values you get, go ahead and like find them and then put them again from least to greatest. Make sure you separate each value with a comma and make sure you include the set of parentheses. Now, here we're going to work backwards. We have the Pythagorean triple, but we need to know our x value. If you think about it, A, B, and C, you know C gives you the largest number. So why don't we know what C is, x squared plus 1. So we're trying to find x. In this Pythagorean triple, 17 is your largest number. So for you, based off of the information we know about C, we're going to say it's x squared plus 1 equal to 17. All you got to do is isolate your x. Here, you want to get x squared alone, subtract 1 on both sides. That cancels. This is x squared equal to 17 minus 1 is 16. I don't want x squared, I just want x. We're going to take the square root of both sides. So then we have x is equal to 4. So we already found our x value, that is 4. Again, repeat the same step. First 37 there. So now that you're all set for that one, let's go ahead and move on to the next one, which is part D. So they did notice a pattern there. So it says examine the set of Pythagorean triples, look for patterns. So like I said, math has patterns in some way. There's always a pattern there that we can try to figure out. So let's take a look at this one. So it says look for the pattern that is true for each triple regarding the difference between the 3 values. Describe this pattern. So you're going to take a look at those Pythagorean triples and find some type of connection. And what not only will you like try to find that connection, you're going to explain that pattern. So it says then see if you can think of another Pythagorean triple that does not follow the pattern, but it is a Pythagorean triple. So if you take a look at it, if the x value is 3 and we're squaring it, right? If you square the value of 3, we get 9. Do you see 1 less than 9 is 8? 1 more than 9 is 10? Kind of following this rule here. So do you see how your last 2 digits in the Pythagorean triple is 1 less and 1 more than the value, x value squared? Let's try it here. 4 squared is 16. So 8 and 10 were used. 1 less than 16 is 15. 1 more than 16 is 17. 15 and 17. There we go again. And the very first digit is the x value times 2. So again, I kind of pointed out the pattern. I want you to go ahead and go ahead and explain what I just explained down below in for part D in the text there. So again, do your best to put it into your own words, describing that pattern. Or if you find another way to go ahead and describe it, or you see something else differently, by all means, go ahead and put it there. Now, the second part to this is that they want you to determine a Pythagorean triple that does not work in this situation. So again, go ahead and take a moment to go ahead and apply that rule there and fill that out for part D. So for the second part, you are going to be playing around a little bit with numbers. And let's go ahead and take a look at this one here. So it says the Pythagorean triple 5, 12, 13 can't be generated from the identity of x squared minus 1 plus 2x squared is equal to x squared plus 1, which has only one variable. Because the length of this hypotenuse is 13 and the length of the longer of the other two legs is 12 units and are not 2 units apart, find a two variable identity by incorporating the second variable y into the variable identity. So based off of this equation here, we're going to apply the y. Now, remember, for anything with a Pythagorean theorem, we need to have a plus sign here in the middle. Because remember, it is a squared plus b squared equals c squared. So do you see here? I can already eliminate this one because there's a minus in between. The idea is also, again, pattern, right? If you take a look, they're replacing the 1 value with a y. So it's x squared minus 1. Here we should have x squared minus x squared plus. That is already eliminated there as well because it's not following the same pattern here. X squared minus y squared. So that looks good. 2x, 2xy, 2xy equals, should be x squared plus whatever number there is. X squared plus, this one checks out. This one's x squared minus, this does not work. So again, process of elimination, you're trying to match the best one there. So, and also you can kind of get your confirmation from part F because they restate the equation that we selected from up above. So find the missing x and y value and the Pythagorean triple using the identity x squared minus y squared plus 2xy squared equals x squared plus y squared. So very similar, right? We know that we can go ahead to find the Pythagorean triples, which is going to be the very first row and the second row. You're going to plug in these values. So if we kind of stick to the same idea, a is going to equal to x squared minus y squared. Again, you already have your x, you already have your y, just plug it in. Your b is equal to 2xy, and your c is equal to x squared plus y squared. Keep in mind, you're not actually squaring the last part. You're not squaring it. You're just plugging it in for A, B, and C. That is for the first and second row. So you can go ahead and do that there. Make sure again with your Pythagorean triples that it's in or you're gonna have 3 numbers there. Separate them with 3 commas. Again, least to greatest. If not, the when it's getting scored, it's actually going to take it as wrong. So again, make sure it's from least to greatest, and you have those commas in between to separate them. Again, don't use any spaces. I don't think I mentioned that one on the other chart up above. Don't put any extra spaces. Just leave it all crammed together, just like how they left it right there. Okay, so Let's go ahead and take a look at this next one here. So here they're actually telling us they gave us an x value, and then for the second row, the third row, they gave us a y value. What we can go ahead and do is choose the largest side because again, we know what our large side is. It's the x squared plus y squared idea. So if we know that c is 41, we can plug it in here. So this is 41 is equal to x squared, or in this case here, 5 squared, plus y squared. Now, here we just go ahead and simplify, right? So for this one right here, we're going to go ahead and do, so this is still stays as 41 equal to 5 squared is 25 plus y squared. I'm trying to isolate y squared. So what I'm going to do is I'm going to subtract the 25 on both sides. So minus 25, minus 25. This cancels. I'm going to move this over. 41 minus 25 is 16, equal to y squared. Now, for this one right here, what we're going to go ahead and do is I don't want y, I want y, or I want y, I don't want y squared, so I'm going to take the square root. So we have y equals, what is the square root of 16? That is your answer for this one right here. You'll follow my same steps using this one, but again, for the next one, you'll use the largest side, which is 45. And then that is the end of this task. And I think the end of the whole course activity. So again, that's just an overview. It's only specific to this course activity. You'll see those identities over again in the future, and you've already seen them already in the past. Binomial theorem and Pascal triangle are not going to come back. And don't go, so make sure you go ahead and save and exit everything, and then open it up again and submit it for score to your teacher. Okay. All right. We're done with this course activity.